So today we're going to do volumes by cross sections. This is section 6.2 in the text if you want to refer to it for extra examples or some extra practice. In the previous section, we saw how to calculate areas between curves. In this section and in the next, which is actually closely related, it's volumes by cylindrical shells, we're going to build on this to calculate volumes. Let's first consider how areas and volumes might be related to each other using solids you're well familiar with. On the left, we have a rectangular prism. Maybe it's a cube, maybe it's not. And on the right, we have a right cylinder. Let's say the rectangular prism has dimensions length, width, height, and the cylinder has dimensions r for radius and h for height. Well, we know how to calculate the volume of these. The volume of the prism is length times width times height. The cylinder's volume is pi r squared times height. Something kind of interesting happened here. In both instances, we have some quantity multiplying height. Well, for the prism, we have length times width, which happens to be the area of the base. In the cylinder case, we have pi r squared times height, but pi r squared is also the area of the base. Now, that's not the only thing these two solids have in common. In this case, if we look at the base and we extrude upwards, it's the same throughout. And if we, again, if we do that for the prism and we do that for the cylinder, it's the same cross-section throughout. Now, the observation we just had where it's base area times height is a special case of what's known as Cavalieri's principle. Effectively, what Cavalieri's principle says is, given a constant cross-section, the volume of that solid is the cross-section area times height. So there's two components to this. One has to have a constant it says it has to have a constant cross-section. This means that the cross-section shape is the same all throughout. So it's all circles, it's all squares. It can't start as a circle, end up as a square, for instance. It has to be circles throughout or has to be squares throughout. But also it's a constant cross-section, so the dimension cannot change. So it's always a circle with radius r, always a square with side length s. It cannot change. It has to be the same throughout. So, but what Cavalieri's principle says, the volume is just the cross-section area times the height in that situation. And one way you can think about it is, no matter what the base is, so no matter what shape, maybe it's a kidney shape or something, or maybe it's a pentagon, something. If you just straight up extrude it upwards, well, the volume, it kind of makes sense that it's just the base area times the height. We're actually going to adapt Cavalieri's principle for our purposes in a little bit. So perhaps somewhat surprisingly, the following two shapes actually have the same volume. Now, if you look at the squiggly pyramid or prism, you might think, depending on the way you think about things, maybe it's less or maybe it's more, but they're actually the same. The reason is they have the same cross section. I constructed this in GeoGebra for them to have the exact same cross section. So Cavalieri's principle says these volumes are actually the same. And the way I like to think about this is that they have the same cross section and they have the same height. So imagine that the red prism represents a giant stack of cards. So maybe it's hundreds and hundreds of cards. And then what we do is we take that nice perfect stack and then we start to push them one way or the other. Well, they're all still playing cards, so their cross-section area doesn't change. It's still just the area of the card. And since we're just pushing, we're not deforming it any, we're just reshaping it, the volume's not going to change. So this is one way I like to think about how Cavalieri's principle says it doesn't really matter how you get from A to B. It's just the height times the cross-section area. Now let's consider a different shape. Now we have this cone with a quarter cut out of it and continuing all the way up to the point. What kind of cross-section do we have here? Well, we have all kinds of different cross-sections. Some are better than others. And what we want to do is we want to think back to the example with the prism and the cylinder. We want to use some sort of symmetry of the problem. We don't want to just pick some random cross-section. Well, here the cross-section that makes the most sense, that's kind of constant throughout, no matter how you move from left to right, up to down, corner to corner or something. This is the correct cross-section. So if we think about the base and we think about it coming up to a point, well, it's going to be the same cross-section throughout. It's just that it gets scaled down until it reaches the tip. And this kind of looks like Pac-Man. All right. Now, what about for a sphere? Well, no matter how we cut a sphere with any plane, no matter what orientation we take, it's always going to give us a circular cross-section. So we could end up with something like this. Or we could have something like this. Or here. They're always circles. So if we want to calculate the volume of a sphere with cross-sections, our cross-section is always the same. It's always a circle. We'll return to this in a minute. All right. So when computing the area under a curve, we used Riemann sums, and particularly Riemann rectangles, to approximate the area. Then we shrunk the widths to 0. In other words, we split up our interval more and more and more. We added more and more rectangles. That meant the widths went to 0. We're going to do something fairly similar here, except instead of using Riemann rectangles, we're kind of going to use Riemann slices, volume slices, to approximate the total true volume. So let's say we want to approximate a cone by slices. We have a cone here in purple, and in the very light green, kind of like the seafoam green here, fairly see-through, we have these wafers stacked on top of each other coming up to a point. We can calculate all those volumes because that's a simple shape. They're just little cylinders. We can calculate each individual volume and we can add them up. Now, if we only used a few of these, it's not going to be a very good approximation. So we need to add more and more and more to get the true volume. And notice here we have a bunch of overestimation. We have all of this out here, all of this out here, and that continues around the cylinder. So this, this is an okay approximation, but we can do better. And the way to do better is we keep adding more and more slices. All right, so that's a cone. Let's look at a sphere, or really a hemisphere. Again, we can use some cylinders stacked on top of each other. We have these little wafers that are stacked. We can calculate their volumes, add them up to get an approximation for the true volume. In this case, we have a whole mess of overshoot up here. So we would have to use a lot of slices to get a really good approximation to the volume of a sphere or a hemisphere. So in this course, we're going to be a little bit limited simply because we're limited to single variable integration. So we are going to be limited to solids that have a fixed cross-section shape. Size could vary, but it's always circles or it's always squares. you never have any where it starts as a circle, ends as a square. We don't have the tools really to do that in this course. In 243, you'll be able to do that with the tools of multiple integration to calculate volumes of solids that are a bit more abstract than what we work with here. Right. So the volumes of our slices, they're just from Cavalieri's principle, it's just our area, whatever our cross-section area is, maybe it's a circle, times a little thickness to give us a little wafer, a little cylinder. So a single slice, we just take the area. Now this xi here, xi star, is just some sample point in the middle. Just like with Riemann sums, we can pick a left sum, we can pick a right sum, or we can do a midpoint sum, or we can pick anything in the middle. Same thing here, we can pick these at random. So we have our area, which will depend on x or y. Times a little thickness, just like in Cavalieri's principle. But that's only one slice. We need many slices to get an approximation to the volume. So our volume approximation, well, we add them up. So in the previous example, our approximate volume, we have one slice here, we have another, and another, and another, and another, and another, and another. We add up all of the volumes of those slices to get an approximate volume. Now, outside of very specific examples, any finite number of slices is not going to give us the true volume. So we need to shrink this width down to 0. Or in other words, we need to add more slices. And this is where the Riemann sum kind of kicks in. We need to shrink the width of each slice, which means we're adding more and more slices to get better and better approximations. And in the limit, this is going to be the true volume. So in terms of Riemann sums, taking the limit, this was our approximate volume. Taking the limit is going to give us the true volume. But based on Riemann sums, we know that we can rewrite this. We can rewrite this expression in a different notation. This is the definite integral. But unlike with Riemann sums, here before we had our function values, our y values. Now it's areas. But that's really the only real difference. So volume is the integral of area, and we'll see this again when we do volumes by cylindrical shells as well. Now, the only thing that's really strange here is what do these limits of integration mean? And it kind of depends on the problem. If there's inherent geometry to your problem, you use the geometry of the problem. But if I give you functions, then you have to return to what we did with the area between curves and look at the intersection points. And that will tell you what your endpoints of integration are going to be, your limits of integration. Now I have some steps I like to follow for doing these problems. One, I like to draw a quick sketch of the solid and a cross-section with all of the relevant dimensions. So, if it's a sphere, put the radius of the sphere on there. If it's a cone, put the base radius, put the height. And also do the same thing for your cross-sections. Depending on what your cross-section is, if it's a circle, you should probably put your little radius for your cross-section. Or if it's a square, put your side length on there. Step 2, I like to determine what the cross-section area expression is going to be. So if it's a circle, it's pi r squared. But we need to turn that into a function of our integration variable. So we need to somehow relate little r, for instance, to x or to y, depending on how we're approaching the problem. Step 3, establish the limits of integration. If you don't have limits of integration, you're only doing part of the problem. You don't know where it's going from and to. And then step 4, actually set up and evaluate the integral for the volume. Now, you don't need to do these in any one order. You can switch 2 and 3 if you want, but I think this is a pretty good flow because it makes you think about this as you build up the layers. All right, so let's do an example. Let's show that the volume of a sphere of radius big R is 4/3 pi r cubed. You know this formula, you've seen it since maybe 6th or 7th grade, something like that. You may never have actually seen the derivation before. Let's go do it. So let me draw the sphere, first of all. Okay. Now, it doesn't matter how we orient this because the cross section is always going to be a circle. Now, let me draw the great circle here. All right. And here's the center of the circle. We'll need that in a moment. And let's draw the radius. Okay. So we have our solid, but now we need to draw a cross section. Like I said, it doesn't matter how we do that because it's always circles. So what I'm going to do is I'm going to do vertical cross sections just because then it'll make my integration variable x. But you could do horizontal and then your integration variable will be y. That's okay. So let me draw a circle here. Now, we still have to label our cross section's dimensions, and the relevant dimensions for the cross section is just the radius. And I'm going to call that little r. All right, so we have our first step done. We have our solid drawn. We have a cross section. Now let's write the area of our cross section down. Well, area of a circle is pi r squared. But that's not in terms of x. So what does x represent in our drawing? X represents where our cross section is located. So here, this distance represents x. So we need to somehow come up with a relationship between r and x and maybe some other variables, some other constants. Well, to do that, there's actually a right triangle hiding right there. All right. So the definition of a circle is it's all the points that are the same distance away from a central point in a plane, though. Spheres is the same idea, but in three-dimensional space. Every point on the sphere is the same distance from the center. So this point here is a distance r from the center, but so is this point here. And we actually had a right triangle hiding, and we knew its radius, or its hypotenuse, sorry. And the hypotenuse is the radius of the sphere. So let me redraw that just because it got a little cluttered. So what we have is something like this. We have our hypotenuse, that's the radius, big R. We had our little r. Actually, let me change colors here. Try that again. There we go. The height of the triangle was little r, and then the distance along the bottom side was x. It was the distance from the center point, center of our circle, or our sphere. All right, so we have a right triangle, which means we can do Pythagorean theorem to relate r and x to each other. So from Pythagorean theorem, big R squared is little r squared plus x squared. And we're really close to having our area in terms of x. Now, what you could do, we want r by itself. So I'm gonna subtract x squared from both sides. So r squared minus x squared is little r squared. And you might be tempted to square root, but notice we have r squared here, we have r squared here. You don't need to do the square root because we're just going to undo it anyway. So we can just take our little r squared equation here in terms of x and plug it into our area formula to get area as a function of x now. And it'll be pi times big R squared minus x squared. All right, so step one done. We did the, we drew our solid and we drew the cross section and all the relevant dimensions. Step two, we got our area formula in terms of our integration variable x. It's x because they're all stacked up this way. We're adding them up this way. And now step three, we need to figure out what our limits of integration are. Well, if we're on a sphere, we go, the furthest left we can go is our units. So our leftmost x value is negative r. And if we go to the right, the furthest right we can go is positive r. So our volume is going to be an integral from minus r to big R of a of x dx. So step three, done. And now all we have to do, plug in our area formula and evaluate. So volume is going to be minus r to big R of pi big R squared minus x squared dx. Now, it is very important that you have your integration variable listed here with your dx, because that tells you what changes. Everything else is constant as far as the integral is concerned. While r is a variable, we could plug in any number we want for it. It's the radius of the sphere. The radius of the sphere doesn't change. So as far as the integral is concerned, big R is a constant. So when you do your integral, it's not going to be 1/3 big R cubed. It's a constant, so we're going to get an x squared, or r squared x. One thing I like to do is I like to move my constants out front. So I'm going to move my pi out front before I evaluate. You don't have to do that, but I like to do that. All right, so now we can do the integral. R squared is a constant, and like I said, that is a constant. So when you integrate a constant, we're going to, if we do the antiderivative, we're going to get that constant times x. And you can think of that as power rule. So that's pi r squared x. It's a constant, just throw on x. But now the next term is a function of x. It's x squared. So that's just the power of x. We can apply power rule. What power rule says is that the integral of x to the n dx is 1 over n plus 1, x to the n plus 1 plus c. Of course, plus c, don't forget that. We're doing definite integral, so it doesn't matter. Plus c would cancel. Provided n does not equal -1. That's the natural log situation. So here, the way I think about this, we're integrating x squared. So we need to increase the power by 1. So we'll go from x squared to x squared, x to the 2 plus 1, so that's x cubed. And what we do is we divide by that new power. I think this is the most foolproof way, especially when you're doing fractional powers. You know, dividing can get kind of tricky. So I like to think about increasing the power by 1 and then dividing by that new power. So we're going to get minus 1/3 x cubed evaluated at our endpoints, our limits of integration, minus r to big R. And now all we have to do is plug and chug. So that's pi, and I'm going to keep pi factored out. I'm going to use some square brackets because I'm going to leave the upper limit in one set of brackets and lower limit in another set of brackets. So r squared, we don't touch that. And then we replace x with big R, so that's, r squared times big R, we replaced x with big R, minus 1/3, replace x with big R, that's r cubed, minus r squared. But now, when we're evaluating at the left endpoint, the lower limit, it's times negative r, still minus 1/3 negative r cubed. And you want to be very careful when you're working with negatives with the fundamental theorem of calculus. You can have multiple negatives on each other, so there's a lot of room for mistake. Just be very careful. All right, this first term, this first part will become r cubed. Here we'll have an r cubed, but it'll be negative because of that negative. And then here we have negative, and then 3 more negatives, negative, positive, negative, positive. So this will be pi times r cubed minus 1/3 r cubed minus negative r cubed plus 1/3 r cubed. And notice that these two terms are just negatives of each other. And we have this negative here. Like I said, if you're not careful, you might end up accidentally canceling these and ending up with 0 as your volume. We know that's not right. So just be very, very careful. This part, we have an r cubed and we're taking off 1/3 of an r cubed. We're left with 2/3 r cubed. There's our 1/3, there's our r cubed. We're getting pretty close. Minus, and now this is negative 2/3 r cubed because they're negatives of each other. And if you fully simplify this, negative, negative, positive, this becomes 4/3 pi r cubed. So we know the volume of a sphere, hooray! Even though we knew that already, it's kind of cool to see. 6th grade you is super impressed with yourself for figuring this out. All right, now let's do a cone. And we're going to do a right cone. We'll see on group work how to do stuff that's not necessarily a right cone, or stuff with a base that's not necessarily a circle. We'll do one with a square base, and we're going to do something that's maybe oblong or like peanut shaped, and it'll be a little bit more abstract. All right, so we have a right cone with base radius big R and height big H. So let's draw that first and foremost. Oh, let me change colors. There is big R. Let me pull that out here. And then here is H. And since it's a right cone, this is actually a right angle. And that'll be relatively important. Not super important, but it's useful to realize. All right, so now we have to actually think about our cross section. We want the cross section to use the symmetry of the problem somehow. And there's 2 obvious directions to try. We could try going horizontally so that our cross sections are vertical. But if we do that, our cross sections would look like this. And that's not something that's necessarily going to have a nice area. It's not necessarily a circle or a semicircle, so we can't necessarily easily get the area of that. So a better choice, and I mean, you could go corner to corner, but that would be worse. A better choice would be to do horizontal cross sections, because if we do that, since this is a cone and cones are rotationally symmetric, we're going to have a circle again for a cross section. And now what the circle does, starting at the base, it'll be its biggest, and then it'll come up to a point. And let's say the radius of the circle is a little r. We need that because we need to know what the radius of the circle is, or the area of the circle is. It's pi r squared, so we need the radius. And as I just demonstrated, as the cross section moves up, the radius is going to shrink. So radius is a function of height. And I'm going to denote this as having a height y. So since our cross sections are stacked like this, we're stacking them up this way, our integration variable is going to be y. All right, so we have our drawing, step 1 is done. Step 2, area. Area is pi little r squared. But our integration variable is going to be y, so we need to relate r to y somehow. Now it's perhaps not immediately obvious, but the way these are related are by similar triangles. So that's a right angle. Let me draw my cross section. So here we had the big radius, all of this, whoops, slightly off. All of this was big H. This was little r, and this was the height of our cross section. So there actually are two similar triangles here, and they're kind of staring at you in the face. That's a right angle because we have the cross sections are perpendicular to the height, and both share this angle, which means that these two angles are also the same, so they are indeed similar triangles. So let me redraw this because it got a little cluttered. Let's do the big one first. Big R, big H. Now I'll put the right angle there. Then we have our smaller one. Little r, right angle. But we don't have this side length. A priori, we didn't define that to be part of the problem. So we need to be able to find what this is. So if we track that back, it is this height, this distance, this length. Well, we know the overall, we know this portion, we can get this portion by subtracting them. So this is actually big H. Oh, let me move that over. Big H minus y. And now since these are similar triangles, we can set up ratios of corresponding sides to get r in terms of y, little r in terms of y. So we have little r over h minus y. This side divided by this side is going to be the same ratio as this side divided by that side by definition of being similar. So it's big R over big H. And now to get little r in terms of y, all we need to do is cross multiply. So it tells us little r is big R over big H times big H minus y. And now we can get our area in terms of y, and that's what we needed. Area as a function of y is now pi, it's little r squared, so it's r over h times h minus y squared. And I'm going to distribute the square, but I'm not going to FOIL. And there's a good reason for that, which I'll explain in just a second. So it'll be big R squared over big H squared, and I'm going to combine that with pi. And then times h minus y squared. I'm just going to leave that as is. And the reason I'm leaving that as is if you FOIL, you will have 3 terms. And then when you do your integral, you're going to have 3 terms for one limit of integration, and then 3 terms for the other limit of integration. That's a lot of terms to keep track of, which means there's a lot of room for error. So I'm going to leave it as is, and I have a different plan in mind. All right, so setting for our volume, well, we have our integral, but we don't know where to integrate from to yet. So if we start with our cross section all the way down here first, and then bring it all the way up there. Well, we're starting at the base. We might as well say that that height is 0. Y starts at 0. And then it goes all the way to the top, but that was a full height of big H. So volume is going to be the integral 0 to big H of area as a function of y, dy. So all we have to do now, step 1, done. We drew the picture. Step 2, we got area as a function of our integration variable, done. Step 3, we have our limits of integration. Step 4, plug it in and evaluate. So that'll be pi big R squared over big H squared times H minus Y squared dy. And again, it's really important that you keep your d blah on there. So dx or dy or dt, whatever it happens to be. Because that's telling you what variable is changing, all of the others are constant. Big H doesn't change, it's the height of the cone. Big R doesn't change, it's the base radius of the cone. Those things are constant as far as the integral is concerned. So what that means is I'm going to factor this stuff out of the integral. And again, you don't have to do that, but I like to do that just to declutter a little bit. All right. Now, like I said, you could FOIL this expression. You could distribute it. You'll have 3 terms, which means you have 3 terms to integrate. That's not too bad. They're all going to be powers of x, or powers of y rather. So the integrals will be easy. But then when you evaluate at the endpoints, you might have a lot of terms to shuffle around. So I'm going to do something a little bit different. And what I'm going to do is I'm going to do a little u sub. So remember, with u sub, u should be the function that's inside of another function. Well, if we look here, the thing inside of something else, well, we're squaring something in parentheses. So a good candidate for u is the stuff in parentheses. So u is going to be h minus y. And then du, we take the derivative of the right side. Big H is a constant. It's the height of the cone. It's not changing. Our cone is fixed. So that's gone. And then we just have the derivative of y. That's going to give us a negative dy. In other words, dy is negative du. Okay? So we'll be able to replace our dy immediately. And this stuff will become u. So we'll just have u squared. That's pretty nice. But since we're doing a definite integral, we need to change our limits of integration. So let's plug in the upper limit. If we plug in h for y, we're going to have big H minus big H, and that's 0. Okay? If we plug in our lower limit, we'll plug in 0. We'll have big H minus 0, and that's h. So it's like we're integrating in the opposite direction. Our lower limit, so we're starting at h, and then we're going to 0, which if you remember, integrals are signed areas, direction matters. That would technically give us a negative volume. But this negative will take care of that for us. It won't be a negative volume. So replacing, our upper limit gets replaced with 0, our lower limit gets replaced with h. And now this is just u, so we just get u squared. And dy gets replaced with negative du. And we can use that negative to switch our limits of integration. You don't have to do that. You could do the antiderivative, factor out the negative, do the antiderivative, plug in the endpoints. It'll work out the same. But I'm kind of particular and I don't like integrating right to left. So I'm going to use that negative to my advantage. And now we just have the integral of u squared. Again, we can use power rule because it's just a power of our integration variable, which happens to be u in this case. So we increase our power by 1. Well, u squared will become u cubed, but then we have to divide by that new power. So that's where our 1/3 comes from. So we have our 1/3, our pi, we have an r squared. Maybe we got the right thing. So we have let me do it this way. I big R squared over big H squared times 1/3 U cubed evaluated from 0 to H. And if we plug in our lower limit of 0, well, it's 0 cubed. 0 cubed is still 0, so we don't need to worry about the lower limit. Now we have to worry about is the upper limit. And when we plug that in and simplify really quickly, we'll get 1/3 pi r squared h. Because we'd have an h cubed, but then we had an h squared in the denominator. So we're just left with the single factor of h now. All right, so those two examples were some basic geometry that you've seen for a long time. We knew the volume of a sphere. We knew the volume of a cone. You may not have seen it before, but we knew the formula. I'm going to throw something a little bit different at you now. So I'm going to do y equals x and y equals x squared. And I want to look at the region enclosed by those two functions. And then I'm going to rotate that around the x-axis. So what I need to do first is draw these things to see where what region I'm interested in. And this is why I said that this connects to the areas between curves. We need to figure out what the region is. We'll also probably need to do points of intersection and some stuff like that that tees right off of area between curves. There's x and there's y. And what I like to do is since we're rotating about the x-axis, I like to do a little loop to remind me which direction I'm integrating or rotating about. All right, so I'm going to use this dark blue for y equals x, and that'll look like this. Approximately, doesn't have to be perfect. And I'm going to use red for y equals x squared. It doesn't have to be perfect. Mine obviously is not perfect. And I want to rotate that about the x-axis. So first I need to identify the region that we want. And the region enclosed by those two is this region. That's the part that's bounded and stuck between those two functions. So that's the part that I want. And I want to rotate that about the x. Well, if I rotate something, it's going to have some nice circular symmetry. And I'm actually going to scale this up a little bit. That way my drawing comes out a little bit better. And I'm going to use this color for our solid. So first, what I'm going to do is the piece that's on the outside is going to be the y equals x piece. So it'll look kind of like this. And then the piece on the inside is going to be the y equals x squared part. So it'll look a little bit like that. A lot of these are going to look like some kind of flower shape, like maybe a lotus or a horn shape, vase, things like that. And our solid will do that. So this guy kind of looks like it's nice and flat on the outside and then curved on the inside. And I'm going to draw a cross section. So draw a cross section over here. Now, there's something a little bit different about this versus the other examples we've done. The difference is that this cross section, since we rotated, it has circular symmetry, so it's going to be a circle. But we do not want this portion. We only want the portion that's stuck between those two functions. So we only want this. And we're excluding this stuff here in the middle. So what our cross section looks like is the following. Clear all that up. This is what our cross section kind of looks like. So this thing in mathematical jargon would be called an annulus. It's a disk with something punched out of the middle, but typical calculus language is a washer. It's a washer. It looks like, washer, the tool or mechanical object. So we want to get the area of this thing. Well, this is two circles. There's an outer circle, there's an inner circle. And so there's an outer radius big R and an inner radius little r. And the area is going to be pi big R squared. But then we need to subtract out that inner part. So we need to subtract the inner circle's area minus pi little r squared now. All right, so what do big R and little r represent? Well, here is big R. It is the distance from the axis of symmetry to the outer function. And again, this ties into the area between curves. We had to determine what was our top function, what's our bottom function. Well, here, what's our outer function, what's our inner function. And then here we want our inner radius. Well, that's the distance from the axis of symmetry to our inner function. So this is little r here. All right, now we have everything drawn. We can piece this together. And let me make all that red. Well, that's okay. So area, or big R, is going to be, it's the distance from the axis to the outer function. Well, that's just the y value of our outer function. Our outer function is y equals x. Our y value is just x. So big R equals x. Little r is the distance from the axis of rotation, which is the x-axis, to our inner function, which is y equals x squared. And it's the y value, so it's little r is x squared. And now here, I drew my cross section vertically. That's because when I rotate this way, the symmetry is about the x-axis, which means that my cross sections are going to be stacked up like this, and they're all going to be circles or washers or annuli, however you prefer. So my integration variable needs to be x in this case because I need to add them up this way. If I did any other direction, it's not going to be nice, and the cross sections are not going to be very nice, and we don't have the tools to do it that way. But if I integrate this way, my cross sections are all going to be annuli with varying inner and outer radii. Okay, so now we can come up with a formula for our area. That is pi. I'm going to factor out the pi because both terms have pi on it. And it's big R squared, so that's just x squared. But then I need to subtract the little radius, the inner radius squared. Well, that's x squared, so that's x to the fourth. So step one, we drew the solid and a cross section. Step two, we have our area formula. Step three, we need to determine our limits of integration. It's kind of obvious that 0 was one of them based on the drawing, but let's go get them. And to do that, we need our points of intersection because we need the points where both curves have the same x and y values at those points. So we need to set x equal to x squared. Now, you may be tempted just to cancel x, but when you do that, you possibly eliminate solutions. So don't do that, don't cancel. You want to move everything to one side, factor, do quadratic formula, do completing the square, whatever. So here, I'm going to move the x to the other side. We'll have x squared minus x. Now, we can do quadratic formula over here. It's a bit overkill, completing the square, really overkill. both terms, there's only two terms, both of them have an x, I'm going to factor the x out. So we have x times x minus 1. The first term has an x left over. The second term was just an invisible 1 multiplying the x, so we have x minus 1. Now, using the zero product property, we have two numbers multiplying to 0. The only way that can happen is if one or both happen to be 0. So that tells us x is 0 or x minus 1 is 0, which tells us x could also be 1. This does not work for any other number. If this was any other number other than 0, you can't do that. This is the zero product property of real numbers. If it was 1 to 100, a Googleplex, you can't do that. Only if the thing on the left-hand side or the other side, whatever happens to be, is 0. All right, so we have our limits of integration now. So that's step 3. Step 4, set up the volume integral and do it. So it's the integral 0 to 1 of area of x dx. So that's the integral 0 to 1 of pi x squared minus x to the 4th dx. I'm going to factor out my pi. Again, I like my constants on the outside. You don't have to do that. 0 to 1, x squared minus x to the 4th dx. And these are, again, just powers of x. We can do power rule. X squared, we increase the power by 1, we get cubed. So we need to divide by 3. X to the 4th, we increase by 1, we get x to the 5th. So we need to divide by our new power that gives us 1/5. So we have pi times 1/3 x cubed minus 1/5 x to the 5th. By the way, from something that looks like 0 to 1. There we go. And again, if we plug in our lower limit of 0, we're going to have 0 cubed, 0 to the 5th, doesn't matter. We plug in our upper limit, we have 1 cubed, 1 to the 5th, that's both 1, those are both 1, so we just get pi times 1/3 minus 1/5. If you want to see the details, I'm happy to redo that if you'd like. And if you want, you can leave your answer like this. That's perfectly fine. The rest is simplification with arithmetic. I don't care about that. But if you want to make a nice common denominator, you can. To simplify the subtraction of fractions, the lowest common denominator is 15. So that'll be 5 over 15 minus 3 over 15. You'll get 2 over 15. So you'll get 2 pi over 15.